In each matrix, there are just two players. They are opponents. They are playing against each other. They take actions at the same time. So choose a row, choose a column, and it decides what happens. So what happens are two things. One gives the reward to the other, or one gets the reward and the other minus the reward. Here are the numbers 1, 2, 2, 0. And the second thing that happens is a stochastic transition. So in this case, if you play top and left, right, you either stay with probability half or you move to the other state with probability half. This dynamic goes on forever, and they move through the states, they get a sequence of rewards, and they will have an objective that collects all this sequence of rewards, and one player wants to maximize it, the other player wants to minimize. Any question with the model? Yes. So action A for one player, B for the other player. That's A is a row, B is a column. And yeah, yes, good. Now, slightly simpler, because it will come up. This is also a concurrent game, zero-sum, just two players, but it's deterministic. So this probabilistic transition will just point to one other state. And it's even simpler because it has only rewards 0 and 1, and the maximizer player wants to reach the 1. Once you reach the 1, you're done, happy forever. So this is a kind of famous example with more states in the middle, but you start here in the bottom, and let's think what the players should do. So if the row player, which is the maximizer, plays top, you play top, and this is kind of the safe option. The opponent can play left, and you just stay there forever, but you never go to this bottom state where you definitely lose. Row is the maximizer. Yeah. Then if for some reason the opponent plays right, you go continue. If for some reason the opponent only plays left, then you can take this risky option, which is bottom. And if the other player is playing left, you continue up. If not, you lose forever. We will see that the optimal strategy in this sense will be playing top for a lot of time and then playing bottom, taking a bit of risk with very small probabilities. So these are concurrent, zero-sum, deterministic games. Any question with the example? No? Great. So there will be different types of objectives, from simpler to more complex, let's say. First is the reachability. You just want to get to a state. Fine. Discounted, what does it mean? You have this sequence of rewards, and you aggregate them in a discounted sum. You care more about the present than the future. Then there is parity. Parity that models any omega regular objective. So, for example, the player 1 wins the game if this state is visited infinitely often. Or this state is visited infinitely often, while this other state is visited only finitely many times. So kind of very, for me, qualitative objectives. I mean, it's still quantitative because the player wants to maximize the probability that this omega regular objective is satisfied. But it's very yes or no, black and white. It's kind of reachability. So this is parity. Then there is the stateful discounted, which is the main objective that I'm dealing with. It could be kind of the original discounted model where the discount factor depends on the state that you are. And that's everything there is. So I'm just saying that the discounted payoff of a run, sequence of states and actions, is a discounted sum where you take the value of today with the discount factor of the state and then go to the future. The value, as usual, is going to be the supremum of the infimum. You can change the supremum and inf. Game theory, this is classical value. What is maybe not so classical is this limit here in the bottom. Lambda 1 and lambda d correspond to a partition of the state. So in a set of the partition, I have one discount factor, and I will take all those discount factors in those states to 0 at the same time. Okay. Why do I care about this limit of stateful discounted when all I needed was just one discount factor? Well, what happens is that parity objective, which for me seemed like qualitative objective, actually happens to have a linear reduction to this limit of a stateful discounted objective. That was surprising to me, maybe for you too, meaning that in limiting objectives, you can consider omega regular, but you can consider this kind of limit, and you're considering all objectives there, basically. Good. So these are the objectives. The question is, I want to approximate the limit value. How hard is it? Again, parity is going to be a special case of the limit value. A peek to the results is going to be, well, previously, the limit value is exponential space. That's the best upper bound. How do we get exponential space? Well, through the theory, existential theory of reals, the number of distinct discount factors, lambda 1 up to lambda d, corresponds to the number of alternation, quantified alternation, and that's where you get the double exponential. Parity is slightly simpler. Through a different approach, you can get a p-space upper bound, but it's still very far in the polynomial hierarchy. So what are the results? From there, we take the limit value, and therefore also parity, to the second level, np to the power np. And from the algorithmic side, what we do is to give an exponential time algorithm. Fine, I mean, okay, but what is important there is that if you fix the number of states, you get something which is polynomial. The parity approach was exponential even if you fix anything like actions or states or actions or a number of discount factors. Number of parities. So that's the result. That's the, oh wow, now you should be surprised. How do we get there? Or what are the difficulties that we have to surpass? First, we care about the approximation and not the computation of the exact value, because the exact value is one, irrational. Okay, but also computing the exact value is square root sum hard, and square root sum is not known to be in NP yet. Now, maybe more important thing is that approximation. So, okay, we care about approximation. Epsilon optimal strategies even for reachability objectives, they cannot really be expressed in polynomial space, at least in the classic way, because the optimal strategies will require W exponentially small numbers. So if we go back in our example, in this game, if you make it large enough, the probability that you need to take the risk is W exponentially small. So, okay, you cannot work with the strategies directly. What are you going to do? We do something, so that's the question. Previous work, the first one says, well, we solved this question, or they solved the question, right? They solve reachability in the second level of the polynomial hierarchy. So there is a way to surpass these double exponentially small numbers. And from the algorithmic side is not in this setting, but in the limit when there is only one discount factor, you can approximate the value, and this is the best algorithm so far. You can do it in exponential space and time. So our work basically extends these two results. We lift from only reachability to the whole limit of stateful discounted, and the same we do with the algorithm. Just to highlight, this is the formal statement. If you want parity, you can just look at the limit of a stateful discounted. I remark it because it was a surprise for me, so maybe it's a surprise for you. Now, so the parity value is, there is a parity objective, a parity condition, right? Meaning that every reward is integer, and the maximizer player wins the run if the reward, which is given infinitely often, the minimum number which is given infinitely often, is even. Then you win. If the minimum reward that is given infinitely often is odd, the opponent wins. The parity value is what's the maximum probability with which you can guarantee that this objective is satisfied. So these examples of, I want to reach this state infinitely often while avoiding this state infinitely often, or only get finitely many times there. Right? And this expresses any omega regular objective. Okay, so before you drove off and say, okay, anything else from the talk is going to be technical about this stateful discounted that I'm never going to look again, there's one technical tool that I want to share with you. It's about root of polynomials. So you know how they are used in algebraic numbers. If you bound the degree and the coefficients of a polynomial, let's say a real polynomial, one-dimensional, then the roots are separated. Roots cannot be arbitrarily close. Good, fine. Maybe you need this at some point for multiple variables, and there should be some extension. Yes, but it's not about the separation of roots, because there can be a one-dimensional space of roots. For example, take the xy plane and just take the projection over y. So the whole x-axis is just zeros. So there is no root separation. You cannot do the same with the y-axis. So, okay, and you can take x plus y or x minus y, and you have the diagonal. So what is the extension of the root of separation of polynomials in one dimension to many dimensions? There is this region where there are no roots. This region comes in the form of a hedge, and it's exponentially small, and then exponentially small, and then exponentially small on each of the dimensions. We are going to take sequential limits, so this is going to be useful for me. But in any case, if you find any other application, you don't have to do the proof again. Given a polynomial, many variables, there is a region which is root-free. Yeah, good to know. So now to the ideas of more these concurrent stochastic games. So I start with the algorithm and then go to the complexity. For the algorithm, I said there is this algorithm for the limit of one discount factor. So I'm going to try to present the main ideas. I'm going to only talk about reachability, and the discounted is going to be discounted reachability. So the payoff is going to be 1 if you get to the target, discounted over time, the value, the maximum that you can guarantee. Great. So how do these ideas work in this setting? So the small notation, the thing is, you fix stationary strategies for each player, sigma and tau. You fix stationary strategies because in the discounted setting, stationary strategies can be optimal, or there is an optimal strategy which is stationary. And in the discounted setting, everything is simpler because there is this discount factor, and there are nice characterizations to play with. This is also exploited in reinforcement learning. So what is the whole characterization? So fixed two strategies, sigma and tau, you get a Markov chain, and the value of this Markov chain will satisfy an equation. The equation is going to be a fixed point equation, which also defines an operator which is contracting. So this is where value iteration comes. You just iterate this operator, and you eventually will get to the fixed point, which is the discounted value. Here it's written in matrix form. Once you have this observation, you say, well, this is just a system of equations, linear equations, so you can solve them. Remember, I'm fixing sigma and tau. We're working in a Markov chain. So the value of the discounted value for Markov chain is going to be given as the quotient of two determinants of two matrices, right? So good so far. Now, this equation, let me linearize it and get to the zero equation at the bottom. Now, we want to solve this equation. We don't know the value. What are we going to do? What we're going to do is to define a parameterized matrix game. So there might be many stationary strategies, but let's consider positional pure stationary strategies. So you just choose one action per state. Good. For every player, you choose one action per state. That's your sigma hat and tau hat. And that defines a Markov chain. You can consider this entry, where the nablas are given by the determinants of the corresponding matrix in the Markov chain. This is a huge matrix. This is an exponentially large matrix game. And it is parametric. What's the relationship with the value, and how does it help to compute the value? Right? That's the lemma here. The value is going to be the only parameter for which the value of the matrix game is 0. That's the characterization. And moreover, the value of the matrix game is strictly decreasing on the parameter. So given two bounds, you can do binary search, and you can approximate the discounted value by solving a matrix game, simply a matrix game. So we have a discounted stochastic game, maybe a stateful because this extends, we extended, right? And you want the discounted value, well, construct a very large matrix game, solve it with a guess. Is it large? Is it not too large? And then you do binary search, and you get an approximation of the discounted value. That's the whole idea of the algorithm. So now you can approximate the discounted value. What about the limit value? Well, more or less the same characterization gives you another result, which is the discounted value as a function of the discount factor is a rational function by parts. And that's why, because you have an expression for the rational functions, you can give a bound on what is the discount factor, which is sufficiently small to approximate the limit. So if you want the limit value, well, take a discount factor small enough. How small? Doubly exponentially small. And then you will get an epsilon approximation of the limit value. So far, so good. So we can approximate the discount factor. We can approximate the limit value by considering small discount factors. And this is the state of the art for limit value in concurrent stochastic games. So if you want to approximate, let's say, reachability, you consider the discounted reachability, this discount factor, which is sufficiently small, you construct the matrix game, and you use binary search to approximate. That's the algorithm. For the complexity. For the complexity result, of course, the ideas are different. I said the matrix game is exponentially large. This is going to be exponentially space. So there has to be something different. We have a game, right? And we want to approximate the limit value. There are two players, and there is an NP guess and an NP oracle. So what is the most natural thing to do? Well, you will guess epsilon optimal strategies. To verify that they are epsilon optimal, you will ask the oracle for an optimal counter strategy. And once you have a guess and the oracle answer, you will get a Markov chain and you fix it. And all you have to do is to compute or approximate the value of this Markov chain. Then you can roll back and verify the epsilon optimality of a pair of strategies, because one is going to give you the lower bound, one is going to give you the upper bound. If they are epsilon close, they are epsilon optimal. So far, so good. The thing is that, again, this deals with the strategies. So I said that we cannot guess the strategies directly. So let me remind you, the theorem is you need double exponentially small numbers to be epsilon optimal. So how are you gonna guess strategies? Well, the double exponentially small is required, but it's also sufficient. So you don't need smaller probabilities. And what do you do with double exponentially small numbers? You use floating point. What if you guess a strategy in floating point? Okay, I don't know. If you fix a strategy in floating point, you will get an MDP, which also has a counter strategy. It's going to be pure and stationary, so you can also ask the oracle to solve that. And all you have to do is to approximate the value of a Markov chain with floating point transitions. Yes. And that can be done in polynomial time. So this is the work of 2013. We also extended. No, this is not extended. This is fine. You can solve Markov chains in polynomial time even when they have floating point. You approximate their value. So as a summary, the TFNP complexity is given by you approximate the limit by a discount factor, you convert the discounted objective to a reachability objective, and you use previous literature. For the algorithm, if you want the limit, you consider a discount factor which is small enough, you construct the matrix and use binary search. Thank you.
So, I think the instructions are that I should ask a question to the audience, a very simple one, in fact. Thank you very much for your talk, which was very stimulating, also for the technical tip that you gave, a very interesting problem. But the question is, of course, we are here because we want to reach objectives. So how many objectives did Raimundo have? And please state which are the objectives. So who the first person to answer this?
I think reachability, then discounted sum, then stateful discounted sum is the fourth, but third was stateful something. And parity also.
So how many?
Five.
I had only four. I had only four. But is anybody else? Does anybody else? No, you can say.
So it's 4 or 5, depends. It's fine. So at some point, there's one slide with a fifth one.
Yes.
So I think
So, so I think he would, okay, no. Well, he was the first, so you give me your name then, because then I have, I think, to register. So we have a few minutes for questions. And we have plenty of microphone.
Thank you for the talk. Do you expect the problem to be hard for kind of levels higher than NP, something like exists are hard?
Say it again.
Do you expect that the problem will be somehow harder than NP, like hard for the existential theory of the reals?
Right. Do you expect square roots to be NP?
It's a good counter question.
Now, so the exact problem is a square root sum hard, right? And that might be its own complexity class. Now, this is the approximation, so it's easier. For 3 years, I expected to be NP and tried to prove that it is NP. The proof failed. So I still expect the approximation problem to be in NP.
Thank you.
I was intrigued by your concept of the zero free zones,
Yeah.
root free zones.
Yes.
So what is exactly the general result that you have proved for a polynomial?
So
Yes. Because
you have a polynomial with bounded degree and bounded coefficients. These are all integer coefficients. And let's say that it has a root on 0. You want a region where there are no more roots. So because a root, in our case, a root of polynomials means that something happens in some dynamic. So you want to ensure that as you change the parameters slightly, no such phenomena exist. So you might have roots on the x-axis, you might have roots in the y-axis, but there's this root-free zone. From the origin, you go to an exponentially small number in one dimension, and then to yet another exponential, not double exponential, but you multiply again by an exponential to in each dimension that you want to walk. And this generates this hedge form zone where there are no more roots. No roots allowed there.
starting from the origin, so the hedge always.
The hedge starts from the origin, goes in one dimension.
But the origin can be a root.
Yeah, the origin can be a root. That's fine. So this is an open set where there are no roots. Yes.
And this was not open.
This was not.
No.
Oh, yeah. We didn't find it. I mean, we hope that it was somewhere, but we didn't find it.
If there are no more questions. So let's thank, if there are no more questions, let's thank the speaker again. Very broad. So the next talk, one of the volunteers can help me, please. The next talk is an online talk, is that right? Yes, please.
Hi, everyone. So there are poster sessions going on outside. It is part of the RHPL sessions. So once you get a chance, please do visit those posters right outside after the session or whenever you're available. Thank you.
Hi, Patricia. Thanks for joining. Could
Yes,
you turn on
I can
the,
hear you. And you?
yeah, could you please turn on your camera and share the
Oh,
screen?
yeah, sure. I forgot this. Try to find. Where is it again? Yes. Is it okay? Can you see me on the slides?
Yeah, we can see you, but please share the screen also.
I did it, but maybe I can restart. But you cannot see my mouse. Okay, I have no mouse. Okay, can you see my slides? Is it okay?
Yeah, now could you please share the screen? Yeah, perfect. We can see.
You can see. Okay, good. Oh. Okay. Okay, is it right now?
Yes.
If yes, I will start. So,
Oh.
so sorry not be able to be there with you in India, but so I have to do the talk online. So my talk is about infinite Markov chains, and it's a joint work with colleagues from France, Benoît Barbeau and Serge Haddad. So the purpose of this work is to design algorithms to estimate probabilities in some in infinite Markov chains with some guarantees. So I will tell you everything about it. So I will review existing approach, and then I will present our approach, which is based on importance sampling and abstraction. And then I will show quickly some empirical studies for this work. Okay, so a discrete time Markov chain is somehow a graph or a game, if you go back to the previous presentation, with only probabilities, so no real strategy for the players. So it's so here I've designed a finite Markov chain, and we can evolve in this Markov chain according to probabilities. Then, so this is a finite Markov chain. And here on the right, I have a denumerable Markov chain. And for those who know a bit about it, it's a random walk with a parameter of 1/4. And these kind of objects are known very well, and we'll use them in the following of the talk. So the purpose is to analyze infinite Markov chains. So in general, they are not given as an infinite set of states and so on. There is a high-level structured model on top of it. So for instance, our studies will be applicable to queues. So queues are like Petri nets. So for those who know Petri nets, you have one which is depicted. So depending on the number of token in the place, you will have a speed of or probabilities of inputs or outputs. I will not go into details here, but these generate infinite Markov chains like this one with rates. And then we will also apply our studies to probabilistic pushdown automata. So here it's a state-free pushdown automaton, so only one state. And we have rules saying how we pop the symbol on the pile, and how we on the push down on the pile, and then it depends on the height of the stack. So we generate also an infinite Markov chain like the one on the right. Okay, our goal is to analyze quantitatively those Markov chains. So in particular, we'll be interested in computing the probabilities for the simplest properties, which are reachability properties. So we are given such a Markov chain, which is finite on the screen, but which will be infinite for us. And we want to know what's the probability to reach to reach a target state, so the happy guy, which is here. So there are cases where we know how to do it because we have closed form formula for the probabilities. For instance, for random walks that I presented earlier, we know precisely what the probability to reach the design state, which is kappa to the n, and kappa is something depending on the probability to go to the right of the random walk, if the random walk is from left to right. But unfortunately, it does not always exist such a closed form for infinite Markov chain. We can also apply numerical methods. So it's a linear system. And if we apply it to this finite Markov chain that we have on the screen, we can find well the probability to reach the target, which is 1/19 in this case. But this kind of method only applies to finite systems, and it's also for big systems prone to numerical error. And so what we can, at this point, what we have is that there is no general method which exists for infinite Markov chains. There are classes of Markov chains for which we can do something, but not many of them. And actually, there have been several approaches which are specific to decisive Markov chains that I will recall or present at least. Okay, so first I want to present you mainly one of the main concepts that is useful in this talk, the one of decisiveness. So maybe one for the question at the end, I don't know. But a decisive Markov chain is defined as follows. So we have the target, the yellow guy, and the happy yellow guy, and then we define the red sad guy, which is a set of state from which it's no more possible to reach the target. And now we'll say that Markov chain is decisive from some state if the probability to reach either the happy guy or the sad guy is equal to 1. So somehow there is a gray zone, which is, I don't know if I will be winning or losing. So winning is a yellow, losing is a red. So when I don't know if I will be losing or winning, it's a gray zone. And for decisive Markov chain, we stay in the gray zone with probability 0. So there are a couple of classes of Markov chains which are decisive. For instance, finite Markov chains are always decisive. Probabilistic lossy channel system, probabilistic vast, noisy Turing machines, they are all decisive Markov chains. So I wanted to mention this is a concept defined by Abdullah Ben-Henda and Mayer quite some time ago. And we have also Markov chains which are not decisive. So there is this one, but I want to go to the random walk. So if I have if I take a random walk of parameter p, like the one depicted on the screen, we know that if p is smaller or equal to 1/2, then the Markov chain is decisive. It's actually a recurrent Markov chain. And if the parameter to go to the right is larger than 1/2, it's a transient random walk and it's not decisive. So we have in the nature, I would say, decisive Markov chain, but also non-decisive Markov chains. And so I will quickly present two methods that are designed to analyze infinite Markov chains, but as we will see and argue, they are only possible in decisive Markov chains. So first, this is, I would say, a rather obvious approximation scheme. So it's depicted on the right, but maybe I will show it on this the graph. So we start from the initial state S0, and then we look at one step further, and we look if we can reach the happy guy or reach the sad guy, and then we compute the probability of both. And then there is a gray zone in the middle. Okay, we pursue. And we go one step further, and we accumulate the probability to reach the happy guy and to accumulate the probability of the red guy. And there is some gray zone again. We continue, and so on and so forth. And actually, at the limit, we accumulate the probability to reach the happy guy, and we accumulate the probability to reach the sad guy. And we have the inequality on the right. We know that the probability to reach the happy guy is smaller than the probability of 1 minus the probability of reaching the sad guy. So if we compute iteratively such a thing, there is one problem. There is a gray zone. And the gray zone is something somehow that we don't want to see. And if there is no gray zone, which is the case if the Markov chain is decisive, then the approximation scheme that I have depicted converges in the sense that at the limit, those two sequences, the one which accumulates the happy guy and the one which accumulates the sad guy, will converge up to 1 minus, I would say, to what we are looking for, the probability of reaching the target. Okay, but this is only correct. This only converges for decisive Markov chains. So this is a well-known scheme applied to probabilistic systems. And then there is another one, which is statistical model checking. So we sample path from the initial state. We sample a path, and if it reaches a happy guy, we count it by 1. If it does not, we don't count it, and so on and so forth. And at some point, we will return the value, we will give the ratio of the number of winning paths over the number of simulations we have done. And we want to output some confidence interval. And actually, what we realize also with this example is that decisiveness is decisive here, in the sense that we will almost surely stop simulations, each of the simulation, if and only if the system is decisive. Because if you go back here, if I launch some simulation, it may be the case that I stay in the gray zone forever. It will not be the case if and only if my chain is decisive, because I will not stay in the gray zone forever, or at least with probability 0. Okay, so for a simulation, the decisiveness is very important, otherwise you will not terminate. And we have notion of efficiency also if we have more condition on the chain, which is positive recurrent instead of decisive, but I will not go into the details. And then it's usual in statistics, somehow we can have guarantees on this simulation using various kind of inequalities. And the one that we use in our work is Hoeffding inequalities, which is somehow we have given parameters epsilon, delta, n is the number of simulation, delta is the confidence value, epsilon is the precision. And if we have good relation between these three parameters, then we have this inequality on the probability of being far away from what we are looking for after n simulation. And the probability is bounded by delta, and far away means larger than epsilon over 2. And so somehow, if we have good properties so if we want to compute the probability of reaching some goal, it's a matter of simulating a lot of time the chain to get some approximation with some confidence. And this is what I call with guarantees. The guarantee is a confidence interval. Okay, so it's very nice. We have nice algorithms for analyzing decisive Markov chains, but what can we do for non-decisive Markov chains? So before diving into the technical contribution, I want to recall you a method that was designed in the 50s, which is importance sampling. So originally, it was used for evaluating rare events in systems. That's events that happen with very, very small probability and that are very hard to measure in terms of simulation because they are very rare. So the method is very simple. You take your favorite Markov chain C, and you just build another Markov chain C prime, which is called the biased Markov chains. It has basically the same structure, plus some bin, I would say. And what is very nice is that if we, instead of evaluating the probability of reaching some goal, we have some bias that we measure, which is the probability. So this is gamma on the right. So this gamma is some value that we'll give to pass. To pass that n in the happy state, in the winning state, we give the value p over p prime. So the probability in the original chain divided by the probability in the new biased chain. So this is somehow a random variable. It's no more a 0-1 variable. We say 1 if I win, 0 if I lose, but it gives some value, some quantitative value to win in pass on 0 otherwise. And it's very easy to realize that actually the probability we are looking for is actually the estimation of the estimate value of this measurable function. And so it happens that it's now sufficient to compute the expected value of gamma in the new chain. And in fact, in the 50s, this approach was only used for simulation without any guarantees. And my colleagues well, more than 10 years ago, gave some setting where we could have also statistical guarantees based on Hoeffding or like inequalities. Okay, so I want to give more properties of the bias Markov chain. So first, as I said, the expected value of gamma is what we are looking for. And now I will write it shorter, mu of S for this value. And actually, the random variable in C that we are evaluating, it's the probability to reach the target. So it's it's distributed according to Bernoulli distribution. The random variable in C prime is unfortunately distributed according to an unknown distribution. So it will be harder to apply theorems that are known. But in fact, we'll be able to transfer the analysis in C to the analysis in C prime, provided some conditions are satisfied. And conditions are decisiveness of C prime. If we want to apply the algorithm we had before, it must be the case that the chain we are analyzing is decisive. So this is C prime should be decisive, and we should be gamma. So the variable we are evaluating should be bounded. In fact, the variance should be bounded, but let's say that we will show bounded, the variable will be bounded. And actually, we can realize it's not easy to see, but it's not at all easy to see actually. But there is a best choice, which is the one which is written here. If I define C prime as the probability on each transition, the new probability is the former probability multiplied by the probability to reach the target from the target location. So SI, if we have the transition SSI, we divide mu SI over mu of S, and we multiply by PI. So this is the new probability that we use in C prime. Then we realize that the random variable is in C prime is no more is simpler. It can take two values, 0 or mu of S from a state S. But there is a default, obviously, that we need to know mu to be able to compute this Markov chain. So this is not usable. This is precisely what we are looking for. So there is a theoretical, very nice optimal one, but it's not useful. And nevertheless, it's useful to understand the further constructions. So it's another view on the important sampling method, and the one we will propose is based on an abstraction. So you recognize the important sampling with C and C prime, and I will explain how we put probabilities in C prime, and for that we will use an abstraction. So first, it's a technical matter. We remove the part which is we cannot reach F anymore, the target anymore. It's not F, it's a target. And then in the middle, I have C dot, which is an abstraction. And I have a mapping between which maps states of C to state of C dot. So for instance, if the image of S1 is alpha S1 and the image of S2 is alpha S2, the probability that I will put in C prime will be the one which is written here. So you recognize precisely the optimal one we had before, except that instead of using mu, the probability in C that was unknown, we use the probability in C dot mu dot. So this is what is written here. So we define P prime as the product of the probability in C times the probability of reach mu dot of S2 divided by mu dot of S1. So if you go back to the optimal one we had here, I went too far away. Sorry. Here we had the best choice, which was Pi multiplied by mu of Si over mu of S. Here we do almost the same, but instead of mu of S, we take mu dot. So the value is the abstraction. Okay. And to be able to define correctly probability so that P prime is a probability distribution, we need some condition in the that constrain somehow the abstraction alpha, which we call the monotony condition, and it's written in green. Okay, so that's a way we have defined a way to automatically given a Markov chain on an abstraction to define another biased Markov chain with no more, maybe not many things yet. And the idea will be the following. We will instantiate this approach using layered Markov chains. So somehow the example I gave earlier were layered Markov chains. If you have a pushdown automata with a stack, then the layer will be the size of a stack, for instance. If you have a queue, simple queue, it might be the number of tokens, which is a layer, what we call the layer. So I don't want to read this. And as an abstraction, I will take random walks. So the random walk C P dot will be the one of parameter P. Those I told you, we know very well. We know precisely the probability to reach the target. Mu dot is very well known. And if I take, for instance, the Markov chain on the left, here you see this is we have levels which are written like a scale, and then we have the random walk on the right, and we will define the natural mapping between the two, associating to a state of level I, the state I in the random walk. Okay, that's a way to, we can do that. We can define that if we apply our previous method to this, we will have a biased Markov chain. And what we proved for this is that if we do what we have just mentioned, if we do some assumption that I will explain a bit later, then it appears that we have an abstraction, meaning that the monotonic condition is satisfied. We can define the Markov chain C prime, and it happens that it is decisive. It is a decisive Markov chain. So the concept, the crucial concept that we wanted to do. And moreover, it's a bonus. The expected time to sample an execution will be finite. And the condition for this is P, what we call P divergence. And P divergence means somehow that first the random walk is a diverging one, obviously. Otherwise, converging random walks are not very interesting for abstractions because the probability to reach the target is always 1. So there will be no impact on C if we apply a converging random walk. But okay, we take a random walk which is diverging, and we assume that the parameter to diverge, so P, is smaller somehow than what happens far away in the original Markov chain. So we assume that for a state which has a level very large, larger than some n0, then the probability to go further in the levels is always larger than P. So P is smaller than P plus in what we wrote here. And in fact, I thought I had something. Okay, in fact, this is related to congestion in queues. For instance, we want that the more somehow we go up in the levels in the random walk, the more we diverge. So this is related to congestion. I don't want to go into this detail, but this theorem is proven using some Lyapunov function. And so, okay, so if we take our example, previous example, so we had our Markov chain on the left, which was not decisive. It's not obvious to see, but it was not decisive. And then we have the random walk in the middle. Then we will C prime on the right, and it happens. We can check it, but the theorem tells us it is decisive actually. Okay, so that was a theoretical part somehow, a bit sketchy, but that was a theoretical part. And now we have done some implementation. Well, Benoit implement these approaches in this tool called Cosmos, which is a statistical model checking tool. And we have applied our approach to some probabilistic pushdown automata. And the methodology is the following. If we have a Markov chain, we first check whether it's decisive. If it is, we can apply our best algorithm on it directly. If it's P divergent, so the congestion thing, then we can use the abstraction, the random walk with the parameter P. And we can apply our algorithm on this abstraction. And we realize also that if we are P divergent, we are also P prime divergent, where P prime is between 1/2 and P. So there will be an interesting question. Is there a best P? Whenever we are P divergent for some P, is there a best value for this parameter? We will see. Okay, so a quick example. So this is a one pushdown automaton as we saw at the beginning. And it's decisive. It's P divergent for every P between 1/2 and 1. And then we have the following experimental results, which are, so the plane line, I don't know if you see them, that the plane line, so the ones that are going to infinity rather quickly, are the approximation algorithm, so the deterministic algorithm. So and the dashed line are for the statistical model checking approach. And we see that obviously statistical is more efficient. It's usual in these cases. And we have tested the algorithm on the original Markov chain on several values for the abstraction for several values of P. And we realize that even if the chain is decisive, applying our method improve the efficiency of the approach. That's what we can see on this picture. And we can make the parameter vary, and we realize also in all cases that there seems to be a best value for the parameter, which is around 0.6. So this is and then we have made a second example where the original chain is not decisive, but is p divergent for every value of p between 1/2 and 1. And we have done similar simulations or analysis. So we see the statistical model checking, which is not flat, but somehow the value of the parameter is not meaningful for this approach, or not much meaningful. But we see that for the deterministic algorithm, that it has a huge impact. And here we'll see that the optimal P in this case is between 0.6 and 0.65. Okay. That's what I wanted to say. So I've presented the general setting for analyzing infinite Markov chains, which happens to be okay for decisive Markov chain, only for different reasons, but decisiveness is very important. We have also shown how we can use the important sampling approach, which was originally defined for rare events evaluation. We have applied it in to turn somehow non-decisive Markov chain into decisive Markov chains. And we have given a condition for our algorithm to be applicable to this biased Markov chain. We have given a general low-level model and given application to probabilistic pushdown automata. We have some quite interesting empirical results. And we also realized that for the examples we made, it may happen that the original Markov chain is decisive, but our method accelerates the verification. And the question is, does there exist a best P? It seems on several examples that there are good P's and bad P's. So we have some guess for the explanation, but it's not so obvious. So we would like to somehow justify this part in a theoretical way. What is the best P and why? And we would like also to apply this to more classes. So thank you very much for your attention, and I'm happy to answer questions.
So thank you very much, Patricia. Now I hear the rule is that the first question is addressed by the chairman to the audience in order to avoid brownie points. So my question is, of course, taken. I'm not asking who is the Russian author that that comes to your mind when you think about Markov. That I won't ask. I will ask her. By the way, who is it? Who is it? It's Pushkin, because Markov started analyzing the frequency of vowels in Eugene Onegin. So, but no, I didn't, that was not my question. My question is, so when is the random walk decisive? Oh, there I saw a hand up. This is to check how.
If the probability of eventually reaching a good state and not reaching a bad state, where bad state means that from there is no path to the good state, is 1, then.
But I wanted to know if in her example, when it's P or for all states is P and 1 over P. And sorry, and 1 minus P. So for what values of P?
Oh, I think it was more than half.
It's not the random walk, but
I
next one.
There's a hand up. Yeah, please.
It's essentially the probability of going left is less than is more than a half.
Is more than half.
Yeah.
Yeah, I think that's correct. Is that, if P is more than a half.
Yeah.
Is that
Yeah,
correct?
Going left is more than
Is
half.
that correct?
Yeah, if P is my P was going to the right, but okay, if P is going to the left, it's correct.
Yeah, okay, I think we can award him the point. Common given. So, thank you very much for the talk. And so now, questions for the speaker. Proper questions now. Please.
Hi, Patricia, Deepak here, can you
Hi.
hear me?
Hi, Deepak.
Yeah, thanks for a very interesting talk. It looks like it can be quite practically useful also to, to use this technique. So I had a question about uh, the, the notion of decisiveness. So if you have a state, like you have this kind of pathological example where you have a state which comes back to itself with some probability.
Yes.
But you can also move on to the rest of the graph where, so let's say the good and bad states are in the rest of the graph. So is this a decisive?
So you loop on the state, and what happens?
And that's one of these gray states, right? It's not
but
a good state.
If your Markov chain is well, you will not loop forever. If the probability is constant to loop, then almost surely you will leave.
Right. So the probability of staying in that state forever is 0.
Yes. So the gray zone will be, yeah.
Okay. Okay. And the other question was, how do you check whether a given infinite state Markov chain is decisive?
There is no general method. There are classes for which we can decide it, but actually very few of them. So no, for the moment, there is no. In fact, I think we don't have any. Oh, maybe we have even undecidability in some cases, in some classes. It's not obvious at all. There is no generic method. So yeah, yeah. So that's why also the method is interesting, because somehow, even if we don't know if the original chain is decisive or not, if we can apply our method, we know that the new chain will be decisive. So this is some guarantee without any effort. So that's also something which is, I think, nice in the approach. We ensure decisiveness without any knowledge about decisiveness of the original chain. But otherwise, there is no generic method.
And finally, how do you check the precision in your experiments? You had the actual, you have the precision of each of the approaches. How do you know the precision? I mean, how do you know the actual reachability probability to measure the precision?
To measure the precision? In which algorithm? In
the graph experiments that you had?
It's how we. I don't understand the question actually.
So in the experiments, I presume you're finding the probability of reaching some state, right?
Yes. Yeah.
And you compute some probability using your technique. How do you know that is?
In fact, just that we record the probability. In fact, for the statistical, we just compute the number of experiments that we need, and for the rest, we somehow we compute until the precision is what we get is below the precision that we fix. And I think the precision that we fixed in our experiment was no, it was the confidence, not the precision. The precision maybe was no, it's not part of the graphic.
X is precision, right? In the previous.
P is not precision. P is a parameter. Okay. The parameter of the abstraction. But otherwise, so I didn't do the implementation, but Benoit had to use multi-precision it was tricky to implement the approximation algorithm because probabilities are very small numbers. And when you add up very small numbers, and if you are not precise enough, then obviously you never converge. And experimented this, and in fact, you can. I think in the paper, or at least in the long version, we explain how we store very small values so that it converges in our experiments. So I don't know if it's your question or not, but that's
I
what
think that,
I can answer.
okay, thanks, Patricia.
Thank you. Thank you.
Oh, now I can answer better. Now I remember. The precision here is the parameter you see in the example. So SMC 01 is the precision 01. Oh, sorry, I was completely out. So here you can, we expect a precision of 01 in green, 002 in orange, and 0005 in red. That's a better answer to your question. Maybe.
Any more questions? If not, then let's thank the speaker again.